Okay, so this one should be another short part. In this part we're going to talk about the control unit up here, and the term control unit is a little bit ambiguous. You'll often see it used to talk about decoders. In this case I'm talking about a program counter control unit, and the reason that it's a little bit more involved than just a simple program counter is because our MIPS machine has 4 different types of control transfers. And a control transfer is how you get from one instruction to the next instruction. So this multiplexer at the top here selects between the 4 of them, and just in order. This first one, labeled 0, is just normal fall through. So you currently have the address of some instruction, you go to the next one. Exactly what you would expect. The one labeled 1 is for branches. Now, branches, as I think we've discussed before, are what are called relative jump instructions, which means that the address of the next instruction is given by some part of the instruction itself added to the program counter. And so, in the case of MIPS, the branch instructions that we have a 16-bit immediate in their immediate field. This is down here. And what we do is we take that immediate, we use it as an offset from the current instruction to figure out what the next instruction is going to be, and we treat it as a signed number. But then also, because every MIPS instruction is 4 bytes, it's always going to be the case that whatever instruction we're jumping to, it's going to start on an address that's divisible by 4, right? Because address 0 would be a valid location for an instruction, so would address 4, but not, or sorry, so would address, address 4, but not addresses 1, 2, or 3. And similarly, not addresses 5, 6, or 7, but 8 would be valid. And so, since we know that the target is always going to be a multiple of 4, and we also know that the current value of the program counter is a multiple of 4, MIPS doesn't waste space storing those 2 bits that are always zeros. So instead, we take the 16-bit immediate, we sign extend it, and then we shift it left 2 positions, and that's happening down here. And this is why we built a half sign extender in the previous part. This is exactly what it's for. Now the output of this half sign extender is called the branch offset, and for a taken branch, the way you calculate the next, the address of the next instruction is you take the current program counter, you add 4 to it, so that gives you the address of the instruction after the current one, and then you add the branch offset to that. And the reason for adding this 4 is sort of a convenience thing, sort of a technical thing. It's not really important. Just the important thing is that this is how the instruction is specified, so this is what we're going to do. And note that I said that this is how you calculate the address for a taken branch, right? Branches are conditional. So for example, one of the branch instructions is BEQ, branch if equal, and it takes 2 registers as arguments. If those 2 registers are not, or rather if the values in those 2 registers are not equal, the branch won't be taken and we should fall through to the next instruction. So somehow our control logic is going to have to check whether or not we should take the branch and change which one of these 2 lines it selects between from the multiplexer. The other 2 control types are a little bit simpler, so just a quick overview. The one labeled 2 is a plain jump, and jump instructions in MIPS are basically absolute. And the third one is jump register, which is completely absolute, so it's very easy. The trick that's going on with the one labeled 2 is that the jump address field of the J-type instructions is only 26 bits. It's not the full 32 bits, so you can't fit the whole address of the instruction in there. However, that doesn't mean that it's, not useful. That's still a lot of bits. So same thing as the branch offset, we know the bottom 2 bits are always going to be 0. So in fact, we actually have 28 bits of the address, we're only missing the top 4. So what MIPS does for those top 4 address bits is it just grabs them from the current value of the program counter. So what that means is you can only jump to the same 28-bit address space as the one that the next instruction is in. But that's not really a problem, because that's like absolutely gigantic, and that's supposed to be bigger than the entire memory segment that the program is stored in, if you're using a standard MIPS memory layout, which we're sort of not because it's inconvenient in TC, but you could modify the machine to do it. So at any rate, we're going to build a little system that just takes all of the appropriate inputs and encodes this logic. And so we're actually not going to build it live. I've done this already, and I don't think it's interesting enough to warrant building live. But we can talk about what we have going on here. So first of all, we have the control type wire. This is exactly the same wire that we constructed in the decoder video, and it's literally just going to go from the decoder and take a straight path up here, or maybe a slightly bent path, but the value on it isn't going to change. One thing to remember from the decoder video is that there was one bit on this wire called link, which tells us that we're supposed to link the address of the next instruction onto into one of the registers in the register file. And that way we can use the value in that register to jump back later, and in this way we can implement function calls. So when the link line is on, we're going to send that as an output along with the address of the next instruction, and the register file will have some control logic outside of it, using these 2 lines to decide which register to send the link address to, if any. And yeah, which address to send the link address, which register to send the link address to, and should it send it at all. Okay, so that's what these do. This little unit is a very simple one. So this one takes the program counter plus 4, ANDs it with this, so this grabs the top 4 bits of the address of that instruction. Then it takes the 26-bit address immediate from the J-type instruction, shifts it left 2 bits, so this way we're moving zeros into these 2 bits down here, and moving the value that was originally there up. And so that way we can get those semantics of sticking 2 bits of zeros on the bottom, and then we OR those things together, and that gives us the output, which is the address that we should jump to. So this one's very, very simple, just a little bit of bit manipulation. This adder takes the address of the instruction following the current one, and it takes the branch offset, and it just adds them. And if we are supposed to do a taken branch, which remember was option number 1, as in the one labeled 1, then we use this value. The jump address that we calculated is going to the option labeled 2, and the option labeled 3 is coming straight from the ALU-A input, which is coming off the register file's read-A output. So this one's for jump register. So finally, the rest of the control logic is just how do we decide what control signals to send to this multiplexer. And so this is where you might notice that the inputs to this multiplexer were coming in a particular order. Both of the absolute jumps were in the upper 2 options, and the things that aren't absolute jumps were in the bottom 2 options. So that's very convenient. It means that the most significant bit of control, which is this one, should come on only when we're doing a jump instruction. So you can see over here with this buffer, we've essentially constructed an OR. So this line will come on if we're doing jump or jump register. And for the other bit, well, if we're not doing an absolute jump, we want it to be off by default and on if we're taking a branch. And if we are doing an absolute jump, then we want it to be off by default and on if we're doing a jump register. And so that's just a bunch of conditions that we can OR together, and so that's going on over here, again, implicitly. So this buffer, which I can move up so that it's a little bit clearer, this buffer is one part of that OR. It's the incoming wire's jump register, and so that turns on the least significant control bit. And then each one of these ands is a condition for a taken branch. So if the control type is branch not equal, and the ALU doing subtraction says that the result is not 0, then that means that the values were not equal and we should take the branch. Similarly, if the instruction is branch equal, and the ALU doing subtraction says that the result is 0, it means that the values are equal and we should take the branch. And then this multiplexer just picks the correct value to send off to the program counter. So this is a pretty simple circuit, all in all. There's not a whole lot of logic here. Part of the reason that we want to encapsulate this in a custom component instead of doing it inline in the architecture is because for various reasons this unit's going to get a little bit more complicated once we do pipelining. And we could still do it inline in the architecture, but it'll be nicer to have it hidden away. So that's all for this part. In the next part, we're going to come back to this diagram, and we have all the pieces now. So in the next part, we are going to put the whole machine together, and then I will show a listing of a fairly simple assembly program, which will have to be written in hex, unfortunately, because the assembler is still not powerful enough to support the normal MIPS assembly, but that's okay. And you can copy the listing of that program to verify that your machine does the same thing that mine does. And in fact, this diagram is basically complete. So if you'd like to give it a shot and try and wire up the full machine yourself, by all means go ahead. My video on that is just going to be literally going back and forth between this diagram and a TC architecture and just trying to copy it and mostly even copy the layout. The only thing that we haven't discussed yet is how to do this instruction unpacking, which is going here. But that's very simple, and in fact I guess I can just show it very briefly. It's just this. So it's just a bunch of byte splitters and byte makers and some 64-bit makers, just manipulating the bits into the right places to get all of those outputs labeled in the same order, and you can see the labels here. So this is the bottom 6 bits, the top 6 bits, the immediate field, whatever that is, whatever that is, whatever that is, whatever that one is, and the jump address for J-type instructions. And so with that, you really could go and just assemble this whole machine. And I would actually encourage you to give it a shot, but in the next video I will go through it in detail. We'll put all the bits together, and then we'll have a full machine, and then we'll be able to talk about pipelining. One other thing that I will note is that we have an extra control signal called signed. So this machine, as diagrammed, actually doesn't make a distinction between set less than for signed and unsigned numbers, and it doesn't support load byte. It only supports load byte unsigned. So I would suggest only implementing what's in the diagram, and then you can take a stab at trying to add those other features, or you can look at the next part to see how I do it. And with that, yeah, I think that's everything.